Hello students, today we shall see what is a linear space or a vector space over real numbers, rather n-dimensional vector space, and also we shall see alternative definition of rank of a matrix, etc. So what is a vector in n dimension? That is vectors in r to the power n. What is r to the power n? Let us see first. Let capital R be the set of all real numbers and n, small n, is a fixed positive integer, and of course we assume here n greater than or equal to 2. Then r to the power n is a set. What is the set? It is the set of all ordered n tuples of real numbers. See, first bracketed x1, x2, xn. This is an ordered n tuple having n components, where all components are real numbers. So this set is denoted by r to the power n. It is the set of all ordered n tuples. If we change the position of x1 and x2, say if I bring x2 first, x1 next, then it is another ordered n tuple. Okay, so this is r to the power n. Now if x is equal to first bracketed x1, x2, xn, that is an ordered n tuple, belongs to r to the power n, then x is called a point or a row vector. It is written as a row, point or a row vector, or simply a vector in r to the power n space, Rn space, n-dimensional space, which is also denoted by this x is also denoted by within first bracket x1, x2, x3, xn without commas. Sometimes we give comma, sometimes we may not give comma. Also denoted by this. Or this x is also denoted by as a column, x1, x2, x3, xn within first bracket. This is an ordered n tuple but written as a column. So in this case, if we write it as a column, it is called a column vector. If we write it as a row, it is called a row vector. Each component in a vector x equal to this first bracket x1, x2, xn is a real number, means x1, x2, xn all are real numbers and is called a scalar. Every real number is a scalar. Two vectors x and y in r to the power n are said to be equal, written as x equal to y. If xi equal to yi for all I equal to 1, 2, 3, n means first component equal to first component, second component equal to second component, and so on. Component wise, these two vectors are equal. The vector 0, 0, 0, n times 0 written with commas, this is an ordered n tuple, it is in r to the power n, and this vector is called the 0 vector. 0 vector, and it is also denoted by the symbol 0. The situation will say whether it is 0 vector or 0 scalar. The sum of two vectors. If x and y are in r to the power n are two vectors, then their sum is denoted and defined as x plus y. X plus y. But what is x? X means x1, x2, xn. Y means y1, y2, yn. So their sum will be x1 plus y1, x2 plus y2, xn plus yn within first bracket. This is also an ordered n tuple. Means we have added component wise. Like matrix, we are adding. Corresponding elements are added. Corresponding components are added. So x plus y, which is also a unique vector in r to the power n, because every component here x1 plus y1, x2 plus y2 is a real number. So this is another vector, unique vector in r to the power n. That is, r to the power n is closed under vector addition. Closure property of under addition. Rn is closed. The product of a scalar k and a vector. Scalar means k, a real number, and vector x means this is an n-dimensional vector x1, x2, xn in r to the power n is denoted and defined as product of k and x. Kx is equal to kx1, kx2, kxn, means k is multiplied with every component. K goes inside. So this is multiplication of a vector by a scalar. This is also a unique vector in r to the power n, because every component is a real number, and that's why it is in r to the power n. Therefore, we can say that r to the power n is closed under scalar multiplication. For any vectors x, y, z in r to the power n, here z means again z equal to z1, z2, zn, order n tuple, and x, y already written there, and scalars alpha, beta in r, it is easy to see that the following conditions hold. What are the conditions? Addition is associative. x plus y plus z is equal to x plus y plus z. Associative. Any two you can add first. X plus 0 equal to x equal to 0 plus x. Here 0 means 0 vector. Minus x plus x is 0. 0 means here 0 vector having n components. Or it can be also written as x plus minus x. Where minus x means minus x1 comma minus x2 comma dot 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 minus xn. All components with negative sign. X plus y equal to y plus x. That is addition is commutative. Alpha into x plus y is alpha x plus alpha y. That is multiplication is distributive. Scalar multiplication is distributive over addition, vector addition. Similarly, alpha plus beta x equal to alpha x plus beta x. Here alpha beta scalar, here x y vectors. Then number 7 is alpha beta x is equal to alpha beta x. Here also associative property used. Multiplication, scalar multiplication is associative here. Alpha beta x is alpha beta x. Then last one is 1x equal to x. 1 is unity, real number 1. So there are 8 properties written and 2 closure properties, vector addition and scalar multiplication. So total 9. The set R to the power n, which is closed under vector addition and scalar multiplication, 2 properties, and also all the above conditions from 1 to 8 hold for all x, y, z in R to the power n and for all alpha beta in R, scalars alpha beta. This R to the power n is called a vector space, which is closed under vector addition, closed under scalar multiplication, and also all the above 8 conditions hold for all x, y, z in R to the power n and alpha beta in R. Then this R to the power n is called a vector space or a linear space. Vector space or a linear space of dimension n. R to the power n is also called Euclidean n space. Euclidean n space. So this is vector space structure. Note, in particular R square, if we take n equal to 2, it is the set of all ordered pairs of real numbers x1, x2 such that x1, x2 are real, is two-dimensional Euclidean space or Euclidean plane. Euclidean plane. R cube equal to set of all ordered triples x1, x2, x3, where x1, x2, x3 are real numbers, is three-dimensional Euclidean space, which is which are both vector spaces, means R square and R cube are both linear spaces or vector spaces, as if we have seen Rn is a vector space. Number 2 note, minus y is actually minus 1 into y. Minus 1 is scalar, y is vector here. So minus 1 when multiplied with every component of y, we shall get minus y1 minus y2 minus yn. X minus y is similarly x1 minus yn, x2 minus y2 dot dot x1 minus yn. Difference of vectors. 0x, here 0 is, this 0 is scalar 0 and x is vector. So 0 goes inside, 0x1, 0x2 dot dot 0xn means it is 0 0 0. So all components 0 means it is 0 vector. This 0 is 0 vector in Rn. Now linear subspace or vector subspace. A non-empty subset W of R to the power n. R to the power n is a vector space, linear space you have seen. A non-empty subset W of R to the power n is called a linear subspace or simply a subspace of R to the power n if W is itself a linear space, itself a vector space under same vector addition and scalar multiplication as in R to the power n. W is a non-empty subset, but it is also a vector space under the same operations as in R to the power n. Of course, the operations will be restricted to W, means you have to take vectors from W only, and of course scalar can be taken from R. So this is subspace. Then a theorem, a necessary and sufficient condition for a non-empty subset W of R to the power n to be a subspace is that alpha x plus beta y belongs to W for all x, y in W and alpha beta in R. This is necessary condition, this is sufficient condition for W to be a subspace. We are not proving this condition, we shall use it. For example, W1 equal to, suppose the ordered pair with elements x and 0, x comma 0, ordered pair x comma 0, where x is any real number, 0 is 0 real number. This is a subspace of R square. If I take W2 equal to order triple x comma 0 comma z, where x and z are any real numbers, 0 is 0 real number, this is a subspace of R cube. In particular, second bracket 0, singleton set with only 0 vector, 0, this is 0 vector in Rn, and r to the power n are always subspaces of r to the power n. Means r square is a subspace of r square, r cube is a subspace of r cube, and second bracket 0 vector singleton set is also a subspace of r square, subspace of r cube. These are trivial. Then linear combination, linear dependence and linear independence of vectors in r to the power n in n-dimensional space. What is linear combination? First, let us see. If v1, v2, vm are m vectors, m numbers of vectors, finite number of vectors in r to the power n, and alpha 1, alpha 2, alpha m are scalars in r to the power r, scalars means real numbers, then a vector of the form alpha 1 v1 plus alpha 2 v2 plus alpha m vm is called a linear combination of vectors v1, v2, vm. v1, v2, vm are n-dimensional vector space. M numbers of v1, v2, vm are m numbers of vectors. M numbers of vectors in r to the power n. That is, every v1, v2, vn has n components. And alpha 1, alpha 2, alpha m are real numbers. And if this type, this is a combination. See, alpha 1 v1 plus alpha 2 v2, scalar into vector plus scalar into vector plus scalar into vector, and this vector, this is also a vector by closure property, this is also belonging to r to the power n, and this vector is called a linear combination of vectors v1, v2, vm. As if in vector algebra we know I cap, j cap, k cap are vectors. See, if I write 2i cap plus 3j cap minus 5k cap, that is also a vector in vector algebra. Linear combination of I cap, j cap, k cap, like that, scalar into vector plus scalar into vector. This is linear combination. Of course, there should be finite in number. Scalars finite in number, vectors finite in number. So this is linear combination. A finite number of vectors v1, v2, vm in r to the power n are said to be linearly dependent. In short, we shall write LD. v1, v2, vm in r to the power n are said to be linearly dependent. LD, in short, we shall write LD always. If there exist scalars alpha 1, alpha 2, alpha m belongs to R, means real numbers alpha 1, alpha 2, alpha m, not all 0. Not all 0 means at least one of them is non-zero. At least one alpha is not 0, such that the linear combination is 0. Alpha 1 v1 plus alpha 2 v2 plus alpha m vm equal to 0. Here 0 means 0 vector. So linear combination 0, but all scalars are not 0. Scalar coefficients are not 0. Then the vectors are said to be linearly dependent. Also, the vectors v1, v2, vm, here better we write m, because in n-dimensional space the number of vectors may be m, any number. M is arbitrary here, not necessarily we take n vectors. Also, v1, v2, vm are said to be linearly linearly independent this time. Dependent already we have defined. Linearly independent. In short, we shall write always Li. If they are not LD, we have first defined linearly dependent. Linear combination 0, at least one coefficient is non-zero. And now we are saying that these vectors v1, v2, vm are said to be linearly independent, Li, if they are not LD. That is, if the linear combination 0 implies all the scalar coefficients are 0. Alpha 1 v1 plus alpha 2 v2 plus alpha m vm 0. Then all the scalar coefficients alpha 2 alpha m should be 0. Then we said that yes, these vectors are linearly independent. That is, they are not LD. For example, let us say, definition will be clear in this example. In R cube, x equal to first bracket 1, 0, 0, y equal to 0, 1, 0, z equal to 0, 0, 1. You can compare with I cap, j cap, k cap in vector algebra, as if we have written I cap, j cap, k cap, are linearly independent, because we can justify why they are linearly independent. Suppose alpha 1 x plus alpha 2 y plus alpha 3 z equal to 0. Here x, y, z are vectors, alpha 1, alpha 2, alpha 3 are scalars, means real numbers. So this linear combination equal to 0, we have assumed. 0 means here 0 vector. Implies substituting the values of x, y and z here, and here 0 vector means 0, 0, 0. 3 zeros, or that triple. Now this alpha 1 goes inside. Definition of scalar multiplication, alpha 1 into 1 is alpha 1 and alpha 1 into 0 is 0, alpha 1 into 0 is 0. So alpha 1, 0, 0, then 0 alpha 2 0, then 0, 0 alpha 3 equal to 0, 0, 0. 3 zeros. Now if we add these three vectors, what you get? Alpha 1 plus 0 means it will be alpha 1. Similarly, alpha 2, alpha 3 order triple equal to 0, 0, 0, and that implies component wise they are equal. Alpha 1 equal to 0, alpha 2 equal to 0, alpha 3 equal to 0, means all the scalar coefficients are 0. All the scalar coefficients are 0. That's why these vectors x, y, z in R cube are linearly independent. I cap, j cap, k cap. We know I cap, j cap, k cap are non-coplanar. That's why they are linearly independent. In vector algebra we used. Okay. Here the concept is abstract. So in Rn, sorry, it should be in R cube. This should be R cube because we have taken three components. In R cube, u equal to first bracket 1, 0, minus 2, v equal to 2, 1, 0, w equal to minus 1, minus 1, minus 2. Three vectors we have taken, u, v, w are LD, linearly dependent, because if we see that minus u plus v plus w, if we add v and w, what we shall get? 1, 0, minus 2, and here it is 1, 0, minus 2, means v and w when added we get u. That's why what I have written, minus u plus v plus w equal to minus 1, 0, minus 2, and these two added, ultimately what you get? 0, 0, 0. All components are 0. Minus 1 into u, minus u means minus 1 into u, v means 1 into v, you can write, w means 1 into w, means scalars are here, alpha 1, alpha 2, alpha 3 are minus 1, 1, 1. Okay, scalars, not 0, but this combination is 0. Linear combination is 0, where coefficients are not 0. All coefficients are here not 0. That's why these three vectors are linearly dependent. Of course, this way of showing linearly dependence is not easy. We shall see how to show linearly dependent or independent later. Okay, this is just an example. These three vectors are linearly dependent. If we side change, then what we shall get? We shall get u equal to v plus w, means one vector is expressed as the sum of two other vectors, or one vector is expressed as linear combination of two other vectors. That's why they are linearly dependent. Like that, for three or for more vectors also same way we can say that if one of the vectors is expressible as linear combination of other vectors, then all these vectors will be linearly dependent. Okay, next comes linear span. What is linear span? If S is equal to a set of vectors v1, v2, vm, set of m numbers of vectors in R to the power n, it is a subset of R to the power n, then the set of all linear combination of vectors in S is denoted by ls. v1, v2, vm are vectors in S, then the collection of all linear combinations of vectors in S. Okay, we can change the coefficients, linear combination will change, and this set of all collection of all linear combination of vectors v1, v2, vm is denoted by ls and is called the linear span of S, which is a subspace of R to the power n. It is a subspace. Already you know what is a subspace. Ls is a subspace of R to the power n. Now, if ls equal to R to the power n, means linear span of S equal to R to the power n, it may be special case. Then this S is called a generating system of R to the power n. Generating system of R to the power n if ls equal to R to the power n. That is if every vector in R to the power n can be expressed as a linear combination of vectors in S, then S will be called a generating system of S. ls means collection of linear combinations of vectors in S, and if this ls is R to the power n, this means that every vector in R to the power n can be expressed as a linear combination of vectors in S, and in that case we said that R to the power n is generated by S, or S is a generating system of R to the power n. And in this case also we say that R to the power n is spanned by S, generated by or spanned by S. For example, in vector algebra, what we have seen, every vector can be written as in terms of I cap, j cap, k cap. If a vector, small a vector is a vector, then we can denote it by, we can express it as a1 I cap plus a2 j cap plus a3 k cap. Is it not? So that's why I cap, j cap, k cap form a generating system of vector algebra. So similar is the case. For example, abstract example, let us see S equal to the set containing e1, e2, en. What is e1? e1 is first component is 1 and all other components 0. e2 means second component is 1, all other components 0. En means last component, nth component is 1, all other components 0. And this set is a generating system of R to the power n dimensional space, Euclidean space. And number 2, the set E1 100, E2 010, E3 001, E1 E2 E3 is a generating system of R cube, 3-dimensional space, R cube. Nothing but I cap, J cap, K cap in vector algebra. E1 is here I cap, E2 is J cap, E3 is K cap. So this is generating system of R cube. Similarly, the set S with E1 and E2, E1 means here 10, E2 means 01, is a generating system of R square, 2-dimensional space. Let us justify Roman 2 by how it is generating system. Let X equal to order triple first bracket A comma B comma C belongs to R cube. Be any vector in R cube, any vector. Then X, we can write this X as A comma 0 plus 0 comma B comma 0 plus 0 comma 0 comma C. If we add these three, we shall get ABC surely. Now this A we can take out, and this A comma 0 we can write as A into 1 comma 0. Similarly, B taken common, it is B into 0 comma 1 comma 0. C taken common, C into 0 comma 1. See, it is A into E1 plus B into E2 plus C into E3. C into E3. It should be E3, not E2. Okay, so A1 E1, A into E1 plus B into E2 plus C into E3 means this is a linear combination of vectors in S. What is X? X is any vector in R cube, but this is a linear combination of vectors in S. That's why this S is a generating system of R cube. Now, what is LD set and LI set? If S is the set containing the vectors b1, b2, vm in R to the power n, means this S is a subset of R to the power n, then S is said to be LD or LI according as the vectors b1, b2, bm are LD or LI. Already we have defined when b1, b2, bm are said to be LD, when b1, b2, bm are said to be LI. So if they are written in as a set, then the set is said to be LD or set is said to be LI according as its vectors are LD or LI respectively. For example, all the sets in the above three examples are LI, means here these three S. This is LI set in R to the power n. This is a LI set in R cube. This is a LI set in R square. These are linearly independent. Now, what is a basis? A subset S of R to the power n means n-dimensional space is called a basis of R to the power n if S is its Li and Ls equal to R to the power n. The set S, it is a subset of R to the power n, it is a Li set, first fact. And second fact, it is a generating system of R to the power n. Then this set S is called a basis of R to the power n. That is a linearly independent generating system of R to the power n is a basis of R to the power n. Linearly independent generating system. Alternatively, a basis of R to the power n can be defined as a maximal Li subset of R to the power n. That is a subset of R to the power n having maximum number of Li vectors, linearly independent vectors, and this number is called dimension of R to the power n. Set having maximum number of linearly independent vectors. That is basis, and this is this n, and maximum number n is called dimension. N. This maximum number is called dimension of the space. For example, the set, whatever already we have written, E1, E2, En is a linearly independent subset of R to the power n, and also any vector x equal to first bracket x1, x2, xn in R to the power n can be expressed as x equal to x1, e1 plus x2, e2 plus xn en. We have seen it for 3-dimensional space. This is true for n-dimensional space also. That is, as a linear combination of vectors in S. This x is expressed so that S is a basis of R to the power n because it is linearly independent. It is a generating system, and this is called standard or canonical basis of R to the power n. Also, maximum number of linearly independent vectors in R to the power n is n, so that dimension of R to the power n is n. This can be shown. We are not showing here. Maximum number of linearly independent vectors in an n-dimensional vector space is n itself, and this n is dimension of n. In R cube, dimension is 3, and 3 vectors are linearly independent. Maximum number of linearly independent vectors is 3. As if I cap, j cap, k cap in 3-dimensional vector algebra, I cap, j cap, k cap are linearly independent, and they are sufficient to express any vector. They are linearly independent. That's why they form a basis. So here, this set E1 100, E2 010, E3 001 is actually a basis of the vector space R cube. Basis of the vector space R cube or linear space R cube. Now we come to what is row space, column space and rank of a matrix. This is second approach to rank of a matrix. Already we have defined in the first lecture what is rank of a matrix. Now we shall see another definition. Let capital A be a m by n matrix having m rows and n columns over real numbers, and let capital R1, R2, rm be the m rows. First row, second row, third row, mth row. R1, R2, Rm denotes rows of the matrix in order. M rows of A and C1, C2, capital C1, C2, Cn be the n columns of A. First column, second column, nth column, like that, columns of A. Now each row of capital A consists of n components. Every row, it is a m by n matrix. So first row will contain n components and can be viewed as a vector in R to the power n. Similarly, each column of capital A consists of m components because there are m rows. So every column will contain m components and can be viewed as a vector in R to the power m. Means every row is a vector in R to the power n and every column is a vector. Every row is a vector in R to the power n. See, m numbers of rows are vectors in R to the power n and n numbers of columns are vectors in R to the power m. The subspace of R to the power n, because R to the power n is a vector space, subspace of R to the power n generated by or spanned by the rows R1, R2, Rm of capital A is called the row space of A. Capital A is a matrix. It has m rows. Every row is a vector in R to the power n, and these rows will generate, means they are linear span, linear combination, collection of all linear combinations of R1, R2, Rm will form a subspace. And that subspace is called row space of A. And the subspace of R to the power m generated by or spanned by the column C1, C2, Cn, n columns, linear combination of all columns, collection of all linear combinations of linear combinations of columns of capital A is called the column space of A. Collection of all linear combinations of columns C1, C2, Cn of capital A will form a subspace of R to the power m, and that is called the column space of A. Now, the dimension of the row space and the column space of a matrix A are same. It can be shown, we are not showing here. Dimension of the row space and dimension of the column space of a matrix A are same, equal. That is, meaning is maximum number of linearly independent rows and maximum number of linearly independent columns of a matrix capital A are same. And this number, this maximum number of linearly independent rows or columns is called the rank of the matrix A. Rank of the matrix A, and we denote it by rank A or row A. Sometimes maximum number of linearly independent rows is called row rank, and maximum number of linearly independent columns is called column rank of a matrix capital A. But row rank of A equal to column rank of A, because maximum number of Li columns and maximum number of Li rows are equal in number. So this is another approach to rank. So rank of a matrix is the dimension of the row space. Dimension of the row space means maximum number of linearly independent rows, or you can say the dimension of the column space. That is maximum number of linearly independent columns. And this is another approach to rank. So another theorem: any set S of vectors containing v1, v2, vm, m vectors in R to the power n containing 0 vector is linearly dependent. Means if a set contains 0 vector, it is surely linearly dependent, cannot be linearly independent. For example, if you can see the proof, if vk equal to 0, where k is a number between 1 and m, any one of them is 0, suppose vk is 0, then 0 b1 plus 0 b2 plus 0 bk minus 1 plus 1 into bk plus 0 into bk plus 1 0 into bm equal to 0. This linear combination is 0. Why? Because all coefficients are 0 and one coefficient is 1 into bk, but bk itself is 0 vector. Bk is 0. So 1 into 0 will be 0, means finally we get 0 vector. Where one coefficient, this 1 not equal to 0. Therefore, at least one coefficient non-zero, linear combination 0, but at least one coefficient non-zero means what? This vectors are linearly dependent. So this set S is LD. So every set containing 0 vector is linearly dependent. Another theorem important, the non-zero rows of a matrix in echelon form are linearly independent. If a matrix is in echelon form, we know what is echelon form, then the number of non-zero rows gives the rank. Actually, why, how, we shall see now. The non-zero rows of a matrix in echelon form are linearly independent. All the non-zero rows are linearly independent taken together. So proof, let capital R1, R2, dot, dot, Rp, R suffix P be the P numbers of non-zero rows of a m by n echelon matrix capital A, beginning from first row where 1 less than equal to P less than equal to M. There are already M rows. Out of them, P numbers of rows are linearly independent. First row, second row, Pth row. These P rows are linearly are non-zero rows. We have to prove that they are linearly independent. If possible, let on the contrary we assume that R1, R2, Rp are linearly dependent. Then, by definition of linear dependence, there exist scalars alpha 1, alpha 2, dot, dot, alpha p, not all 0. At least one is non-zero, such that their linear combination alpha 1 R1 plus alpha 2 R2 plus dot, 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 alpha p Rp equal to 0, means 0 vector here. Now, at least one scalar coefficient is non-zero. So let k be the least suffix such that alpha k not equal to 0, where 1 less than equal to k less than equal to p, means it may be that alpha 1 not 0, maybe that alpha 2 not 0. So first, which one is non-zero, that we have denoted by alpha k. Alpha k is first non-zero coefficient. Then all coefficients after alpha k are 0. Before alpha k, sorry. K is the least suffix, means first suffix for which alpha k not 0. So before that, all coefficients are 0, means it may be that alpha 1, alpha 2 0, but alpha 3 not 0. So first we have got alpha 3 not 0, so it will start from alpha 3. That's why number 1 becomes alpha k, rk, alpha k plus 1, rk plus 1 total alpha p rp equal to 0, because k is the least suffix. Okay, so line number 1 changes. Now alpha k not 0, so if we side change, it is minus alpha k rk equal to alpha k plus 1, rk plus 1 total alpha p rp. Now alpha k not 0, so it will have inverse, reciprocal, real number, so we can say it is reciprocal. Rk equal to minus alpha k inverse into alpha k plus 1 rk plus 1 dot alpha p rp. Now scalar multiplication is distributive, so you can distribute. So we write rk equal to minus alpha k inverse alpha k plus 1 into rk plus 1 plus minus alpha k inverse alpha k plus 2 into rk plus 2 dot minus alpha k inverse alpha p into rp. Line number 2. See, rk, kth row is expressed in terms of k plus 1th, k plus 2th and pth rows. Kth row is expressed in terms of succeeding rows, but the matrix is in echelon form, so this rk is a non-zero row. Let the jth component of rk is the first non-zero element. It is a non-zero row. Rk is a non-zero row of a matrix in echelon form, so it will have a non-zero element. Suppose jth component of the kth row is the first non-zero element, first non-zero entry, then jth component of each of succeeding rows rk plus 1, rk plus 2 dot rp is 0. Why? Because the matrix is in echelon form, and therefore the jth component of the vector in right hand side of number 2, rk plus 1, rk plus 2, rp, all rk plus 1, rk plus 2, rp has jth component 0. So the jth component of the vector in the RHS, means in the linear combination itself, is 0. Jth component in the RHS of number 2 is 0, but the jth component of the vector in LHS of number 2 is not 0. Why? Because it is a non-zero row and we have assumed jth component is non-zero. Thus we meet a contradiction. Why? Because the number 2 is a equality, so every component of vector in the left side should be equal to every component, corresponding component of vector in the right side. So jth component in the of the vector in the right side is 0, because rk plus 1, rk plus 2 dot rp have jth component 0 for all of them, because the matrix is in echelon form, number of zeros increases row by row. So we meet a contradiction, because jth component of left side is non-zero but jth component of right side is 0. Therefore our initial assumption is wrong. That means we have assumed if possible let alpha 1, alpha 2, r1, r2 dot rp are ld. This is wrong, so they cannot be ld. Therefore r1, r2 dot rp cannot be ld, and hence they are linearly independent, Li. So the non-zero rows of an echelon matrix are linearly independent, all the non-zero rows. Now if we include a zero row, it will be LD, already you have seen. So maximum number of non-zero rows, maximum number of linearly independent rows in a echelon matrix is nothing but number of non-zero rows. So we note this. Since the non-zero rows of a matrix A in echelon form are linearly independent, so they constitute a maximal Li set. Because if another row, if you include, it will be zero row, so that will be LD. So the non-zero rows constitute a maximal Li set. Maximal means maximum number, having maximum number of linearly independent vectors. Maximal Li set of vectors, and hence they form a basis of the row space. A maximal Li set is a basis, form a basis of the row space of the matrix capital A, and therefore row rank means rank of capital A is equal to the number of non-zero rows of capital A when it is in echelon form. So we have justified the number of non-zero rows gives actually the rank of the matrix if the matrix is in echelon form. So another theorem, elementary operations do not alter the rank of a matrix. That already stated in the first lecture. So elementary operations do not alter the rank of a matrix. Here the third elementary operation was ith row changed to ith row plus k into jth row. Means it is a linear combination. Ith row replaced by linear combination of ith row and jth row, like that. But row space itself is the linear combination of all row vectors. That's why dimension will not change. Dimension will not change using elementary operations. Okay, multiplying a vector by a scalar is an elementary operation. Interchanging two rows or two vectors in a set makes no difference in the set, no difference in the vector space. That's why elementary operations do not alter the rank of a matrix. So what we shall do, to find the rank of a matrix, we reduce it to echelon form using elementary operations, because rank will not change, and then the rank of the matrix is equal to the number of non-zero rows in its echelon form. So this is the justification why we change the matrix to echelon form and get the rank immediately using elementary operation. Okay, so this is second approach to rank we have seen. Now another definition, elementary matrix. A matrix obtained from a unit matrix by an application of a single elementary operation is called an E matrix or elementary matrix. Elementary matrix, in short, E matrix. Matrix obtained from a unit matrix. What is unit matrix? You know, by an application of a single elementary operation is called an E matrix or elementary matrix. Another theorem, every elementary row operation of a matrix can be obtained by pre-multiplication of the matrix by the corresponding E matrix or elementary matrix. Now another sentence is there, every elementary column operation of a matrix can be obtained by post-multiplication of the matrix by the corresponding E matrix. Means if you apply an elementary operation to a matrix directly, elementary row operation to a matrix directly, and if you pre-multiply the given matrix by the corresponding elementary matrix, you will get the same effect. That we shall just see as an example, not formal proof, just justification, verification rather. Applying R2 change to R2 minus 3R1 means second row change to second row minus 3 times first row to this element unit matrix. This is unit matrix 1 0 0 0 1 0 0 0 1. We get an E matrix, elementary matrix. Suppose it is ER, denoted by ER. So if we operate this operation R2 minus 3R1 means second row minus 3 times first row, so 0 minus 3 will be coming, just minus 3 1 0. Second row is changed to minus 3 1 0, other rows remaining. This is ER. Now consider this is a matrix 1 2 3 3 6 0 1 4 5, arbitrary matrix I have taken A. Now apply this same operation R2 change to R2 minus 3R1 to this capital A. What we shall get? 3 minus 3 0, 6 minus 3 into 2 6 0, and 0 minus 3 into 3 9 means minus 9. So we have got this directly applying this elementary operation to this matrix. Directly applying this elementary operation to this matrix, we have got this matrix. Now pre-multiply this matrix capital A by ER, corresponding elementary matrix, ER into A. You multiply by usual multiplication. This way we know how to multiply matrix by first into first plus second into second plus third into third. We have multiplied, we have got this matrix exactly same as this. These two are same. See, these two are same. So directly applying an elementary operation to a matrix is same as pre-multiplying the matrix by the corresponding elementary matrix. Now if we apply the column operation, you have to post multiply. Let us see verification. C2 change to C2 minus 2 C1 means column 2 change to column 2 minus 2 times column 1. So to this capital A, this A matrix here, if we apply, we get this column 2, second column minus 2 times first column. So 0, 0 and 2 will be coming. To A we get 2 minus 2, 3, 6, 6 minus 6, 6, 0, 4 minus 2, 2. So it will be 2, sorry. It will be 2. Okay. 4 minus 2, 2 into 1, 0, 2. Okay. Now, applying the same operation to unit matrix, we get second column minus 2 times first column. It will be 0 minus 2 and others means minus 2, 1, 0, other thing will remain same. Now multiply, post multiply capital A by this EC, elementary matrix with column operation. So this two, if we multiply this element, let us check this element only. This is third row, second column. If we multiply 1 into 1, 2 into 0, 3 into 0, so 1. Then second minus 2 plus 2 minus 2 plus 2, 3 into 0, 0. Okay. 1, 3, 2, first or third column 1, 0, 2, 0, 3 into 3, 3. Okay. So we have to check only this element. This is element in the third row, second column. So third row, second column, let us multiply 1 into this third row, this second column, let us multiply. See, 1 into minus 2 plus 4 into 1, 4, so plus 2 and 5 into 0, so it will be 2. Okay, so correction done. See, A into EC is equal to this matrix, and these two matrices are same. You can see they are same. Directly applying or post multiplying. So this is the effect of elementary operation and multiplication of given matrix by corresponding elementary matrix, and this will be helpful in finding inverse of a matrix by Gauss-Jordan method, etc. So today only theoretical part we have seen. Problems we shall do in the next lecture, next class. Thank you.